When I receive a packet capture, one of the first things that I like to do is examine the metadata. So let's take a look at some of the metadata on this capture. We're going to go to Capture File Properties. As we can see from the properties, we can see when it was captured. We can see whether or not there were any drop packets, whether any capture filters were in place, the link type, and the packet size limit. Now this packet size limit tells me that there's no frame slicing and that I'm going to be seeing the entire payload. Now if I look at the total number of packets and the time span, 14 packets over 180 milliseconds, it sounds to me like this was part of a larger capture, and I may be able to reach out to the individual that provided this capture to give me a more complete capture. Let's take a look at some expert information. As we can see, we have bad checksums. We have them at the IP layer and at the TCP layer. Now by default you wouldn't see these because Wireshark disables checksum validation. However, I enabled them because I want to make a point. And my point is this. If you see packet loss that you can't describe and you can't find where packets are being lost, perhaps you have a bad TCP checksum. It's rare, but it does happen. Okay. Now, previous segment not captured, common at capture start. DUPAC 1, DUPAC 2, suspected retransmission, suspected fast retransmission. These events may be related to one another. First off, the retransmission and fast retransmission, they're two diagnostics on the same frame. So it's really one frame we're talking about here. But let's say that host A is communicating with host B. And host A sends 3 segments to host B. Segment 1 gets either misordered or lost. That's going to cause host B to send duplicate ACKs once it receives segment 2 and segment 3. Okay, so that would explain that type of scenario. Now the fact that we only see 2 DUPACs makes it a little doubtful that we actually are seeing a retransmission. It's probably a reordering type situation. Okay, but we're going to look at that when we get into the trace. Now in terms of SSL, this is purely informational. But basically what it's telling us is that the SSL session used a session key that was negotiated in a prior SSL session. It's really an optimization. We can also see from the expert info that we see connection establishment. So there may be just one connection in this particular trace, or there may be multiple. We're not sure. However, we know that we do see a SYN and a SYN ACK. Okay, let's get a little bit more information about this capture. Let's take a look at the protocols in use. I mean, from the previous screen, we knew that there was TCP in play, as well as SSL. Let's see what else we got going on. Well, that looks like about it, because every frame we got has a TCP component. We can see there's a total of 14 total packets. 14 of those have TCP. 5 of those have SSL. So at this point we know that all our communication is TCP based. So let's go and take a look at conversations so we could see some TCP information. Okay, so we see that 192.168.1.10, which is a reserved address, is communicating with 52.22.153.18 on port 443. And as we would expect, that's our 14 packets. Our duration is about 180 milliseconds, as we've seen previously. Let's turn on name resolution to see if we can come up with some names. Okay, so our source is slow user communicating with the Amazon EC2 instance, it looks like, and that instance is located in the Amazon East region as shown by this Wilmington, Delaware. So let's take a look at these checksum errors and make sure that these are actually due to checksum offloading. So one thing I'm going to do, and there's probably about a ton of different ways to do it, but I want to show you something pretty neat, is I'm going to go in and select this particular field. I'm going to prepare a filter, selected. So we've got good, false, and we're going to go down to the TCP checksum, and we're going to do, actually we'll do an applies filter, so it automatically applies it. End selected. Okay, so we don't see any bad frames coming from the EC2 instance, or from that direction I should say. And let's just go in here and let's go into endpoints. And this is an interesting feature that I like to use a lot, this limit to display filter. Now we can see that 192.168.1.10 has transmitted a total of 8 frames. And once we turn on the display filter, we still see those 8 frames. So none of the frames have a good checksum. Okay, let's clean this up a little bit. I'm going to get rid of the checksum calculations. So let's go into Protocol Preferences under IP, and we're going to turn off Validate IP4 checksum if possible. And we're going to turn off the TCP checksums. So Protocol Preferences, Validate TCP checksum if possible. Gets a lot cleaner. And we're going to get rid of this filter. We don't need it. Now we notice that our expert information, we no longer see the checksum errors. Let's take a look at the trace itself now. Okay, so we see the client, slow user 1, send a TCP SYN to EC2. EC2 sends a SYN-ACK in about 117 milliseconds, and then we see the completion of the three-way handshake. Now, Wireshark calculates the IRT to be about 118 milliseconds, and it's basically the time between frames 1 and 2 and 2 and 3. So if we add those 2 times together, between 1 and 2 and 2 and 3, we're going to come up with this calculation. Okay, so our connection's established at this point. Next we see the client send a client hello, and this gets acknowledged. However, interestingly, the acknowledgement occurs at 24 milliseconds later. This is nowhere near this this SYN-ACK time. Let's make sure that this acknowledgement applies. I mean, obviously it's 181 is the acknowledgement, which implies that there were 180 bytes of data sent, 234, that's about right. But let's go in and we're going to actually set the next sequence number and apply it as a column. Okay, so the client, on the client hello, the next sequence number would have been 181, so that validates that the ACK coming back is for this particular client hello, which only took 24 milliseconds as opposed to 117 for the SYN-ACK. Interesting. Okay, next we've got our previous segment not captured. Okay, and the sequence number. Let's get rid of this next sequence number. All right, let's add, we're going to add sequence number, which I scrolled past already, right? Okay, sequence number is 1461. Let's add this as a column, apply as column. And we're going to add the length of TCP segment length. Okay, so we see on this first frame that we received by the server, or the first TCP segment carrying data, we see the sequence number is 1461, and it's the segment length is 1460, which is 2921, and then 1049 bytes. Now these two segments, because they're out of order, because we've never received bytes 1 through 1460, generate duplicate acknowledgments. So we've got 2 duplicate acknowledgments, and then we've got what Wireshark sees as being a fast retransmission. However, I'm not sure about that, so let me try and see if I can verify that. So what I'm going to do is add the IP identifier field to our display. Now the IP identifier acts like a kind of serial number. So when packets are passed through IP, IP puts a stamp on them and serializes them. And the main reason for this to occur is for fragmentation. So what we see is an IP ID of 41709 down here and 41710 here. This means that this frame was actually transmitted before this one over here. So these dupacks were generated because frames were sent out of order. And we're not seeing any actual retransmissions because at this point the client sends a client key exchange change cipherspec encrypted handshake message, and the server sends its own. Now the thing about this is at this point, this is where we would see data transfer start, because our SSL handshake is pretty much, our handshake protocol is done. And at this point we're going to see the SSL record protocol. We don't see any of that in our trace. So there's really not enough information in this trace to tell all very much. In future traces, what I'm going to be looking at though is the synact time, and I'm going to be looking at the whether or not we're seeing a lot of frame misordering, and that's actually causing real retransmissions, and that would be a problem. But that's pretty much it at this point. I'm going to have to get some more data, is really the answer. But I've got a couple areas of things that I'm going to keep an eyeball out for. So that's pretty much it. I hope everybody enjoyed this, and I will talk to you soon. Thank you.